Okay, well, today I want to start a discussion on climate change. And see if I can get this guy rolling. There we go. Okay, so we are in section E of the coastal environment section of the syllabus, so that first component of material that we're going through. Um, by the end of this, I am looking for you to be able to describe the influence of greenhouse gases on the global climate, explain how stable isotopes are used in climate science. We're going to spend a bit of time on that today. And then summarize the effects of climate change on coastal ecosystems. So let's get started. All right. So, whenever you're talking about climate, I think the first thing you really have to do is define the difference between climate and weather. And bottom line is, weather is an immediate thing, something that happens in a time frame of hours or days or maybe even weeks, right? But it's short scale. And weather, actually not distinctly different from climate in some ways, is measured by things like wind speed and direction, temperature, atmospheric pressure, precipitation, those kinds of things. Okay. Now, weather is typically identified at a particular place and a particular time, specific to these types of conditions. So think short term and think well, what am I looking for here? Regionally specific. Okay, so we're not going to talk about global weather very often. You're mostly going to be talking about what's the weather where I am, right? Okay. Climate, on the other hand, is the behavior of the atmosphere over a longer period. And so this can range from months to literally millions of years. A lot of times, you'll see climate intervals broken into 30-year periods is fairly typical, especially, if you are watching the current science and evaluations, computer modeling, and that sort of thing are being done. A lot of times they're working in 30-year intervals. Um, Now, you'll hear climate defined in some instances as the average of weather. Um, to a great extent, that's the case of it. Is climate really is the average of weather over a long period of time and over a global scale, right, or a very large regional scale. So you might look at climate in a along a specific continent, for instance. Um, so generally, again, we're talking about climate being the mean and variability of temperature, precipitation, and often wind. Okay. Well, most frequently it's temperature and precipitation, but wind is included in that. So not quite as specific as what you're going to see the weather described in if you're looking at the Weather Channel, for instance. All right. So um, I'm just going to spend just a second on this because you'll probably hear both of these terms. So, climate change versus global warming. There's some overlap between those terms. Global warming really describes the more recent trends in the climate, say over the last 100 to 150 years. But the more appropriate term is climate change, and so that's how you're going to hear me refer to that. Um, and really, climate change describes the long-term changes in the statistics of weather events over a period of time, again, ranging from decades to millions of years. And this might be, again, specific to a region. So, again, we might look at climate across North America, for instance, or more often is going to be global in scope. It's not necessarily, like I said, synonymous with global warming, but you'll hear a lot of times, especially in the public press, you'll hear those two terms used interchangeably. Sometimes global warming is used again to describe really more recent events in the climate as the climate has been warming over those last 100 years or so. Okay. So, whenever you talk about climate change, you're going to hear a lot about carbon dioxide. And so I want to unpack a little bit about why is this so important. Now, to set the tone here, we've understood greenhouse gases, and you'll see this abbreviated as GHGs frequently. So we've understood how they affect the climate dating back at least to the 1850s, right? So there were studies by Eunice Foote here in the United States in 1856. John Tyndall, who probably is maybe a little better known, did some work in Ireland in the 1860s, and they documented the heat capturing effect of carbon dioxide and methane. There were later studies calculating the temperature in the Arctic based on the amount of CO2 in the atmosphere. And there was later work by Nils Ekholm, a Swedish meteorologist, that agreed in 1901 the present burning of pit coal is so great that if it continues, it must undoubtedly cause a very obvious rise in the mean temperature of the Earth. Okay, so why is it so important? Right? Why were these scientists dating back 150 years concerned about this gas, right? And greenhouse gases in general. Okay. Well, greenhouse gases are matter, right? They have mass, they take up space. They absorb energy and emit radiation at a variety of different wavelengths depending on the molecular composition of the different compounds in the atmosphere. So these different gases have different elements contained within their molecular structure, and those different elements interact with the energy primarily transmitted from the sun, but also reflected and emitted off of the surface of the Earth. They react to those things in different ways, right? So solar energy is a range of different wavelengths of both energy within the visible spectrum, light colors that you can see, so wavelengths that you can actually see with your eyes, and then a whole range of those outside of the visible spectra. So everything from microwaves and X-rays to infrared, right? Um, so in some ways, this is good, as we'll see. In some ways, it can be problematic. But what I want you to understand here is that energy in and energy out, if they're equal, okay, so if you consider the atmosphere as kind of the screen, okay, um, the energy that makes it through that screen and then the energy that makes it back out of that screen is important. If you have more energy coming in than going out, you have warming. If you have more energy going out than you have coming in, you have cooling, right? Optimally, you have you have a temperature like we have today, which allows us to farm, for instance. That is stable, right? That it's in homeostasis, that balance is in homeostasis. Okay. Um, the greenhouse gases are good, by the way. We need those because of that balancing effect, because of the nature of what those greenhouse gases do. If we didn't have them in the atmosphere, if we had them to a lesser extent, the Earth would be very cold, right? That would not allow us to probably have developed to the extent that humans have developed on the face of the Earth, as we'll see here as we move forward. Okay. So every year, actually every second of every day, the sun is sending radiation towards the Earth at equivalent to more than 7,000 times humans' annual energy consumption. Okay, so way more than what we as a species use. About 30% of it actually ricochets off of the atmosphere or is reflected off of the upper atmosphere and back out into space. The rest of that then is absorbed or reflected back out after it's reached Earth's atmosphere. Okay, so it's either absorbed in the atmosphere on the surface of the Earth, or then reflected back out into space by these different surfaces. And we can quantify this, and there have been a number of studies that have done that. So warming happens, right? As I described earlier, warming happens when these greenhouse gases act like an insulator and they capture that energy rather than allowing it to escape into space. Okay. Again, there's some good things that are associated with that. The planet being warm enough to be able to support the myriad of plants that we have, for also for the climate to be as stable as it has been over the last 10,000 plus years, has allowed us as a species to develop in ways that probably wouldn't otherwise have been possible. However, too much is not good, right? So in fact, our activities, all that development that we've done since we were cave people, has increased this imbalance. And this is referred to as radiative forcing. Okay. And this has been about half a watt per square meter in the last, say, 15 years or so. And it's mostly due to greenhouse gas concentrations. Okay, actually, that statistic is between 2003 and 2018. Although, to my understanding, that hasn't changed dramatically since that period of time. That's remained somewhat constant. All right, so carbon dioxide is the second most common greenhouse gas, and those greenhouse gases, those GHGs, include a variety of other things, including water vapor, right? Methane, nitrous oxide, ozone, all the chlorofluorocarbons, CFCs. So think refrigerants, for instance. All of those things are common greenhouse gases. Even though water vapor is more common and has a larger greenhouse effect, CO2, carbon dioxide, is the gas that is the one that we're impacting the most, the one that we're creating. And it persists for decades in the atmosphere. Now, methane, which is 25 times more powerful than carbon dioxide in terms of its radiative forcing, um, it persists in the atmosphere, not for as long, but that potency, the difference in its potency, it's 25 times more potent. That means that overall, it can be far more hazardous, especially as the climate is warming and more methane is being reduced as a result of that thawing, particularly in areas that have rich sources of plants that once they thaw start to decompose as the microorganisms and the sediments in the soil start to break those down. So there are certainly concerns. If you look at this graphic here, so you can see how different gases compare to one another. Again, carbon dioxide is the one we're most concerned about currently because it's the one that we have the most direct impact on, primarily through the use of fossil fuels. We're taking carbon out of the soils, combusting it, and then that the combusted waste products are released into the atmosphere, and that's where they can act as greenhouse gases and cause that radiative forcing. Okay, and you can see that here. Carbon dioxide, in terms of our impact, is more than 3/4 of our total impact, much more so than things like methane or these fluorinated gases, chlorofluorocarbons. Okay, so quicker question here. Greenhouse effect is the tendency for the Earth's atmosphere to prevent the escape of radiated heat into space, the tendency for the Earth's surface to trap heat radiated from the Earth's atmosphere, or the tendency of the Earth's surface to release heat into space. Well, if you guessed A, then you are correct. Which of the following might be evidence of climate change? An extreme heat wave and drought in Texas for 3 weeks. A record high temperature on a summer day at the North Pole. Increasing frequency of heat waves on the US West Coast for over a 100-year period. Record low sea ice in the Arctic Circle in 2018. Okay, if you look at the time frames here that we're talking about, the one that best fits this question, that best answers this question is C, increasing frequency of heat waves on the US West Coast over a 100-year period. Again, we talk about climate, we're talking about long time frames, right? Okay. Now, that's not to say that individually or more likely collectively with other evidence that these other things couldn't provide some evidence of climate change, especially if we start to see these things over and over again over a long period of time. But as they stand here, C would be your best answer. All right. So, how do we measure past climate change patterns? Well, there are many different sources of information about paleo climate, which is the prehistoric climate records, and that includes things like fossils, pollen, tree rings, ocean and lake sediment deposits. These things are referred to as proxy data. Okay, so they're not direct measures. We are estimating values based on other data that we're able to collect, right? So we weren't on the planet with sensors that would allow us to measure the temperature and record it accurately a million years ago, right? But there are things that were here a million years ago still today that we can look at that will tell us a lot about what the conditions were at that time and much more accurately than you might believe, right? So we're going to provide on measures of carbon dioxide and temperature today. All right, so a little background. If you look at the temperature trends over, say, nearly a million years, the last 1 million years, right? Um, all in all, the average temperature across the entire surface of the Earth has ranged from a low of a little over 9 degrees Celsius to a high of around 16 degrees Celsius. Okay. And you can see that there has been a lot of fluctuation in the climate over that time. And there are a lot of things that attribute to those. We're going to unpack those as we kind of work through this today. But what I want you to understand is that the Earth's climate has not been stable over this long period of time. There have been short periods of stability, but by and large, the climate has been extremely variable. Okay. Um, Now, if we take a smaller slice, right? So we look just at what you see here, which is this, just kind of where I put this little dash circle here, right at the end. Okay. That represents this last 20,000 years or so. And you'll see that 20,000 years ago, we were in the end of what was the last ice age, which would be this valley right over here, kind of in the left edge of that circle, right? And so we would have been right kind of in this area here. And I want you to notice that, okay, 0 is the average of the temperature across the surface of the Earth over the last 10,000 years or so, okay? Notice that the difference between this average temperature, which is about 15 degrees Celsius or about 59 to 60 degrees Fahrenheit, what you're seeing here is the difference between an ice age and current day climate on the surface of the Earth is only about 5 degrees Celsius, right? It's important you bear that in mind because as we talk about climate and warming, you're gonna see those estimates in Celsius a lot. And unfortunately, here in the United States, because we tend to still utilize Fahrenheit as our primary source of measurement for temperature, most people, right, especially those outside of the sciences, look at 2 degrees Fahrenheit and it's like, okay, that's not a real big deal. And they're right, 2 degrees Fahrenheit isn't a real big deal, but 2 degrees Celsius is a big deal. Okay. All right. So, another thing I want to point out here is that over the last 10,000 years, since we came out of that last ice age, now again, geologically speaking, this is still a short period of time, right? Look at this graph again. But over this last 10,000 years, the climate has reached an area of relative stability. Now, again, you'll see some fluctuations in here, and there are sources for these fluctuations. Again, we'll unpack some of those. Some of them are things that were happening here on Earth. Some of them are things that are happening with the Earth in terms of its what it's doing in terms of its rotations and its rotation around the sun and those kind of things, energy inputs and outputs, all of that kind of stuff. But by and large, it's hovered right in or around that 15 degrees Celsius range. And that allowed humans to do something that they had never been able to do before, right? I shouldn't say they, we have never been able to do before, which was establish stable agriculture in one place. And that allowed us to become, as we entered into our agricultural society, that allowed for us to plant food, provide predictable calorie content. So instead of moving with our food as it went back and forth across the surface of the earth to find the right temperature range based on the seasons, and having to have mobile housing and all that sort of stuff, we could stabilize, and that allowed us, number one, to have a calorie content on a daily basis that we could predict. All right, so that improved health. It also allowed us to start to change the landscape in ways that benefited us, right? So we could have more permanent housing. We could establish cultural centers, communities, right? We could start to trade with one another so people could start to specialize and get good at specific things. And then we could trade with people with things that we weren't good at, right? And that allowed us to develop all the way to where we are today, all because of this change in the climate. All right. Okay. So looking at these graphs, right, knowing that, or here I'm showing you that we've got all of these changes in the range of the climate across the surface of the Earth. How do we know this, right? I'm sitting here telling you this, but how do we actually know it? Do we have data to support this? And in fact, we do. Really good data sets for climate actually come from glacial ice cores. So you've probably heard of the Vostok Glacier. There are other glaciers in Antarctica. These things are over 3,500 meters deep, and they extend back over 800,000 years, right? So this is 8 of those climate cycles. I mean, we're talking about, right, if I'm going to go back a slide here, we're talking about going back to this range, all right? So through all of this stuff, we have ice cores that have, or I'm sorry, ice packs that have been on the surface of the Earth throughout that time frame, okay? The deeper down you go, the further back in time you're going, right? The further back that snowpack fell and was compressed into that very dense glacial ice, right? You know, glacial ice is different than the ice you make in your freezer at home. Right? It's much more dense. It's much heavier. If you've ever if you ever had the pleasure of seeing a glacier, you know that that ice is as blue as the color on my screen right now. Now, here's the thing. When that snow falls and it packs down, it traps air bubbles, okay? And this actually, much like when I buy something and I know I'm not going to eat it right away, so I buy something in the grocery store, what's the first thing I do with it? Throw it in the freezer, okay? That will preserve it over time. Well, this is a much better freezer than what I have at home, right? We're talking about these ice packs. And so the snow, it traps air bubbles and it gets compressed, and this preserves these trace gases from all of these time frames, right? So what you're seeing in these photos here are pictures of how they actually drill these cores down here. And so they get these long tubes of ice that again can go hundreds or even thousands of meters down to get down to where that snowpack dates back, 800,000 years. So what they end up doing then is they analyze these tiny air bubbles in order to determine tropospheric composition. So what was the composition of the gases that were trapped, right? So we can look at the relative amount of carbon dioxide to nitrogen to oxygen, for instance, right? We can look, that can then tell us things about temperature trends. It can tell us about snowfall, forest fire activity. Believe it or not, there is a line in glaciers that, in these Antarctic glaciers rather, that show the differentiation between prior to and after enacting the Clean Air Act in the United States. Okay. That tells me two things. A, how amazing this is at capturing Earth's history. The other thing is how big of an impact the United States alone has in terms of global climate cycles, right? So two bits to unpack there. All right, so here you're looking at an ice core, and you can see some layering that's in here. These show different time frames. You've got a layer of sediment in here as well. You've got some underlying, it looks like an underlying frozen water, perhaps at this part. I'm not 100% sure, but you can see the different layers of this. And what these scientists do is they essentially take these cores and they subdivide them so that they can do different, so different scientists can do different types of analyses, right? So, and the way they divide this up, I'm not sure if there's a method to this or not. This is, I am not a climate scientist, so, and I don't work with ice cores. I work with sediment cores. So, but in this instance, I don't know if there's reasoning behind the way they divide these up, and there's some possibility that different scientists might do this differently depending on the nature of the study. But nonetheless, they divide this up. And what they're doing is they're trying to get some duplication in some areas so they can look at different things, right? And so they'll have one section that is exclusively going to be used for scientists that are going to look at gas composition in the air bubbles that we talked about. There's going to be some that are going to be archived in case we want to go back and look at those again as our technology continues to improve. They'll look at the chemistry of the ice and other contents within the ice. They'll look at isotopes that we're going to talk about today. And also they'll look at the physical properties, things like density of that ice. All right. So, we can look at the change in oxygen, for instance, that is trapped in that air relative to the current air in seawater. And this can be a temperature proxy for us, okay? So we can also do that with deuterium. You probably looked at deuterium in, I would suggest probably your inorganic chemistry courses. And so deuterium is heavy hydrogen, right? And so again, looking at the content in the ice relative to the current standard ocean water, okay, that also can be a temperature proxy for us. And then we can directly look at carbon dioxide in the entrapped air, understanding how that works, okay? Okay, so with oxygen and deuterium, we're talking about stable isotopes here, right? So you guys know what isotopes are. Again, this is something you should have covered in your inorganic chemistry courses. So this is essentially an element. It can be, any number of different elements, but essentially when we talk about an isotope, we're talking about something that's the same element, all right? So it has the same number of protons. But they have different atomic mass values. All right. And those mass values vary depending on the number of neutrons that are present in here. Right. So carbon is, in fact, one of those elements that has some isotopes. And that's part of what allows us to do carbon dating, right? So archaeologists, a lot of times, if they're trying to date artifacts, they utilize carbon. They analyze the ratio of carbon-12 and carbon-13 to try and determine, okay, what age is this? And that's because of the rate at which carbon-13 forms, okay? All right, so different isotopes behave similarly to each other because they have the same number of protons. And remember, when you look at the periodic table, the protons here really are the defining component of an element that determines whether it's one thing or another thing, right? They might, any given element might have different numbers of electrons at different times because of circumstances, and they could have different numbers of neutrons, as we're talking about here. But the protons are the key thing that makes carbon one thing and nitrogen another thing, right? But when nitrogen decays, and one of those neutron or one of the protons in the nitrogen decays and becomes a proton, then you get carbon 13. Okay, so they behave similarly, but the lighter isotopes, right? So because they have a smaller atomic mass, just like you might expect, they would react to changes, say, in energy, which moves matter. They react a little bit more quickly. They react a little more quickly in chemical reactions as well. So this difference in behavior is referred to as fractionation. Okay, fractionation. And a heavier isotope typically is, as I said, it doesn't react as quickly as the lighter ones do. So we consider this to be discriminated against during biogeochemical and biologic reactions. So different processes, reactions, conditions have different fractional rates, and this gives us isotopically different signals that we can measure. All right. Okay. So let's look at isotopes of oxygen. Oxygen normally contains 8 protons and 8 neutrons, right? So it's going to have an atomic number of 8, and its mass is going to be 16. All right. So you can see this would be the common or normal oxygen, right? However, a very small percentage of oxygen atoms contain 8 protons and 10 neutrons. So we refer to this as oxygen 18. So it has an atomic mass of 18, or a little over 18. And so here you can see what that looks like. So it's still got the same number of electrons in its normal state here for this isotope, because it's got those 8 protons. All right, so that the overall charge on that atom is still going to be neutral, but those extra 2 neutrons give it extra mass. All right, so this heavier form is still a stable isotope as opposed to a radioactive isotope, one that decays. Okay, so this is a stable isotope. So it takes more energy to evaporate. It precipitates out of the atmosphere more readily. So it has an environmental fractionation. All right. That's important when we look at global cycles of water, for instance. All right. So let's take a look at that. So when water evaporates off of the surface or through transpiration from plants, right, that water gets into the atmosphere. And this can include both isotopes, right? So you can have your normal oxygen 16, or you can have your oxygen 18, that heavier isotope. But in fact, when you have precipitation, because the water that contains, so again, we got water, H2O. Watch The Water Boy, right? That's what I call quality H2O. So, so you've got, love that movie. So you've got water, H2O, that if it has that heavier oxygen, that oxygen 18, it's going to want to precipitate a little more quickly than water that has, where its oxygen component is oxygen 16. So as it rains, so as precipitation starts to form and a cloud loses that atmospheric moisture back to the surface as part of the water cycle, it's going to lose its heavy water, right, with the oxygen 18 more quickly. It's going to be depleted more quickly than that with the oxygen 16 as its component. Okay. So that's important when we start to talk about the formation of ice packs. So colder temperatures result in higher concentrations of light oxygen in snow at the poles. Okay. And you can see that here in this graphic. So here we're looking at temperature from the warm end to the cold end, from 20 degrees Celsius to minus 60 degrees Celsius. And here you're looking at the variation between um, the time frame and the standard based on what that temperature was. And what you see here is the concentration decreases with temperature of water or this ice that has that oxygen 18 in it. So that heavy isotope of oxygen becomes less prevalent the colder the temperature gets. All right. And so in places like these really coldest places, locations in Antarctica and Greenland have about 5% less oxygen 18 than ocean water. Now, snow is always going to have some percentage, but again, it's going to get the percentage of oxygen 18 is going to be less. So if you look at this plot graph, you can see it's less the colder the temperature goes. It's more the higher the temperature goes, right? So these coldest places are going to have less of that. Okay, follow me so far? All right. So the oxygen 18 in polar ice is always lighter or less than it is in seawater. All right. During an ice age, moist air rising from the equator cools faster, and that's rained out as that air moves closer to the poles, it becomes less. So the amount of O18 in that glacial ice indicates the relative temperatures, what those relative temperatures were at the time the ice formed, right? So how cold it is, again, has an impact. You have less oxygen 18 in that ice during colder periods and more during warmer periods. So I probably should have put this in an earlier slide, but I've used this symbol a few times, right? And so what I'm referring to here, and again, probably something you saw in your chemistry classes, but essentially this represents the ratio in samples of oxygen 18 to oxygen 16 versus the standard in seawater. Okay, so that's what that difference is. Okay, anyway, I think this whole thing of being able to measure these isotopes and use them as proxy data is really, if you'll pardon us, cool. So I can't resist. It's in my nature. All right. So, but I do think it's really remarkable because again, otherwise, our understanding of how the climate has cycled would be so severely limited, right? We can measure tree rings. I have cores in my lab that I can go take cores of tree rings, but even in the oldest trees, that's going to be just a tiny fraction of the Earth's history. I mean, by geologic standards, like we're done, right? From the time that tree germinated to the time it died. Okay. So even cypress trees in some of our swamps that date back several hundred years, again, wouldn't inform us on all these changes that have occurred over millions of years. So this is really an important data set. So hydrogen, as I mentioned earlier, is somewhat similar to oxygen in this way. It has a very similar environmental fractionation that occurs. So the heavy stable isotope of hydrogen is hydrogen 2, right? Deuterium, right? So normal hydrogen, you've got a proton. Remember, hydrogen does not have any neutrons in its normal state. It has one proton, one electron. But here, where you have heavy hydrogen or deuterium, you have a neutron, right? And you still got your one electron, one proton. And this has a higher mass. So, again, a very small fraction of hydrogen atoms um, contain both a proton and a neutron. And here again, the deuterium signals, right? So the amount of deuterium that we're able to find are lighter or less in glacial ice during these colder periods. Okay. So the readings between deuterium and oxygen 18 allow us to extrapolate kind of the relative air temperature when ice was formed. Okay. So we can take that data and we can compare that to air bubbles in the ice core with greenhouse gases like carbon dioxide. And this provides a direct measure um, of the temperature relative to the amount of carbon dioxide that was present at that time. Okay. So again, I just think this is really remarkable. This technology, I think, really has provided us with not only a way to determine what has happened in the past, but also what we can look for in the future as we try and build these models that allow us to predict how the climate might alter based on relative contributions in the atmosphere, our contributions to the atmosphere, rather. Okay, true or false? There's generally less oxygen 18 in glacial ice near the poles during an ice age than during warmer periods. Well, this is, of course, true because the water that contains the heavier oxygen atom is going to precipitate out more quickly, and this is going to be lost before it gets to those polar areas if you look at the way these circulation patterns with water go. The second one here is well, the process where heavier stable isotopes are discriminated against during biogeochemical reactions is called what? This is called fractionation. Okay, fractionation. Okay, so let's talk a little bit about the relationship between past temperature and carbon dioxide. So this graphic displays temperature and on the top, carbon dioxide on the bottom. When you look at this, I think I see a pattern, right? So not surprising. There's a lot of similarity between these two signals, all right? And but one of the things I really want you to notice, and I'm sorry, it looks like my lines have gotten shifted here in this slide, but you can still see when you look at carbon dioxide, for instance, you can see this peak here is pretty high. And this peak here matches up and it's pretty high. But when you look on average, the values here certainly seem to correspond with each other, where you have lower peaks, right, in the carbon dioxide, the peaks were lower with temperature, right? Where you have higher peaks with temperature, there was a higher peak that corresponded with carbon dioxide, okay? A lot of research indicating this. And if you want to look at this, I'm putting some references down there for you to take a look at. This is not just true, however, with carbon dioxide. Remember, I mentioned that there are a lot of factors that impact climate. And there are, in fact, a number of greenhouse gases. Okay, so this graphic, which again you can find for yourself if you'd like to go take a look at it, we've got carbon dioxide here in blue, we've got our temperature here in red, we've got methane here in green. We have the variation in the percentage of atmospheric oxygen 18 here, right? That heavy isotope of oxygen. And then we also have the insolation value. So I haven't mentioned insolation, but insolation is not the same as insulation, right? Insulation is what you put in your walls, or what the greenhouse gases do. Insolation is the amount of energy that is reaching any given area from the sun, right? So the sun's energy, once it penetrates, we measure insolation values on the surface of the Earth to calculate, to give us an idea, like, for instance, how much energy is being moved through an ecosystem. You can use it to determine how effective are my solar panels going to be on my roof, that kind of stuff, right? But my point here is that when you look at this graph, all of the signatures have some overlap. So it's not just carbon dioxide again here that's having this major impact. All of these things clearly are having an impact. The relative amount of impact or direct effect they have on temperature differs from one parameter to the next. but they're all critical, right? All of them have these issues. It's just that we produce our impact. The thing that we control the most is carbon dioxide. We can't control insulation values, right? For instance, the insulation values are largely caused by things well beyond our control, like where the Earth is in its orbit relative to the sun. So you may or may not have looked at Milankovitch cycles. It is interesting, and there's a lot of good videos, more than I could do in the course of this short presentation. But essentially, Milankovitch, let me try that again. Milankovitch cycles include a number of different things, including the wobble of the Earth, the tilt of the Earth relative to the sun, where the Earth is in its orbit around the sun, which is not circular, it is egg-shaped, and that the nature of that egg stretches and kind of goes back and forth. There's also differences in the amount of energy that the sun actually puts out. So all of these things have impacts. And they're cyclic in nature. So one of the things I like about this particular graphic, it actually tells you the differences. So not all these things are even on the same cycle. So that's a whole nother layer of variables that have to be looked at when we're looking at climate changes. Now, there are natural factors that we can't control that happen here right here on Earth as well. Volcanoes are one example that you'll hear a lot in this particular discussion, because volcanoes put a lot of greenhouse gas into the air, especially carbon dioxide. But they also put a lot of particulate matter in the form of dust up in the atmosphere. And that particulate matter blocks the amount of solar energy that can get through the atmosphere, which then offsets that by providing kind of a cooling effect of sorts, because it's in the upper part of the atmosphere. Now, that same dust, when it settles on top of an ice sheet, can actually cause that ice sheet to melt faster, because then it's absorbing energy, right? So again, a lot of things to consider as we're looking at this. It's not a really simple thing. So part of our problem solving and part of how we are looking at what we can do to adjust this is looking at, okay, where are our major contributions? And again, that's why carbon dioxide falls out. We're talking about the atmosphere anyway. So why we focus on these greenhouse gases, and particularly carbon dioxide, is because we're the ones that are really responsible for the major increases since the beginning of the Industrial Revolution 150 years ago. So the increase in any greenhouse gas is going to trap more heat near the Earth's surface, right? And this is going to result in both atmospheric and oceanic warming. And oceans are really important in terms of how the climate functions, right? Because they move a lot of heat around the globe, and they can take heat from one place, that heat energy, and move it to different parts on the globe. That can be good or bad, right? Europe has benefited for thousands of years from a relatively warmer climate than it should have, based on its latitude above or north of the equator. But the Atlantic Ocean, because of the Atlantic conveyor, there's heat energy that gets transferred in the Atlantic Ocean up to that latitude, and that's released into the atmosphere, which has warmed part of Europe's climate. So that can be good, but on the other hand, it can also cause problems like melting the Greenland ice sheet, right? Those kind of things. So again, not super simple. A lot of things going on here. Now, water vapor isn't really changed a lot by human activities. But as you're going to see, water cycles do change as a result of climate change. So while we don't have a direct impact on water vapor, we do have secondary impacts because of our addition of these greenhouse gases. All right, so you can see here in this graphic, when we look at, again, carbon dioxide, a lot of these greenhouse gases are a result of combustion processes. There's a lot of combustion in the production of cement, for instance, but the biggest one really is petroleum, and that has ramped up considerably since the 1950s as more individuals have individual vehicles. There's more homes. There's simply more of us, right, on the surface of the earth, and we collectively use more energy per person than we did prior to the 1950s. And so that's really had a big impact on petroleum. Now, coal, while its usage has still increased, a lot of that increase has shifted from um, uh, Western societies, right, first world countries like the United States, much of Europe, to second and third world countries where their ability to harvest energy, they're kind of still where we were prior to the 1950s in terms of how they produce energy. So coal still has a much bigger footprint. The sad thing is that first world countries are often importing coal to these third world countries. That's problematic. But we're seeing some shifts in terms of energy policy, so more focusing on leapfrogging them past where we went to get them right to more renewable sources that produce less of these greenhouse gases into the atmosphere. Okay, so the reason this is important is because, as we saw before, these waste products, right, these greenhouse gases, when they get up into the atmosphere, a lot of that gas, a large proportion of it, about 40%, stays in the atmosphere, okay, and continues to increase the amount of carbon in the atmosphere to the point where it can be really hazardous. So if you go back to that graphic, one of the first ones I showed you, I had a line on it where I had temperature and carbon dioxide compared. There's a line up there that said 418. That is about where we are currently, right? So that's the amount of carbon in the atmosphere currently. Now, if you'll recall, go back and take a look at that graphic. Historically, when we've had very warm periods, warmer than today in Earth's history, based on our proxy data, the amount of carbon in the atmosphere was considerably less, down in the 380 range or lower. So this is very concerning to us, and we're going to talk about why that is. All right, so how do we know that the increase in carbon dioxide in the atmosphere is due to the release of fossil fuels? Again, I'm going to point to isotopes here, right? Stable isotopes of carbon in the atmosphere. So carbon 12 is the largest one at more than 99%. Carbon 13 is 1% or less. Okay, so plants discriminate against the heavier isotope, which means that there is less carbon 13 in plants than there are in the atmosphere. So fossil fuels are basically old plants. All right. I think I told you before, the joke in class where whenever I stop and put gas in my motorcycles, I always joke to myself, I'm filling up with fresh dinosaurs. The reality is I'm mostly filling up with old plants. So when we look at oil reserves and most fossil fuels, that's primarily plants because of the number of plants relative to animals on the earth. All right. So they typically have less carbon 13 than what you'll find in the atmosphere. And so what we're finding is that the atmospheric carbon 13 is decreasing. So the source of increased carbon dioxide must be light, okay, using that term. So as we're burning more plants with more carbon 12 in them, the ratio of carbon 13 in the atmosphere is decreasing because the amount of carbon 12 in the atmosphere is growing because of the amount that we're putting in. Here's the short story of that. All right, so, and we see this in these isotopic analyses where it shows that the carbon 13 concentration is declining. So this is from a 2018 study. And that's diluting the carbon 13 in the atmosphere. This is very strong evidence that the source of increasing atmospheric CO2 is from the release of fossil fuels, which is the only active source of light carbon in the atmosphere, right? It's the source that's getting up there. That's us, okay? And in fact, that value is much lighter now than it's been at any other time over the last 160,000 years, pardon me, 160,000 years. Okay. So, key points I want you to get from this. Plants fractionate or discriminate against carbon-13, which you'll recall is lower percentage in the atmosphere anyway, right? So only about 1% of the atmosphere. Um, so fossil fuels, which are old plants, don't contain very much of it. They have light carbon, right? The carbon-12 primarily. As light carbon from fossil fuels is released, more carbon-12 than carbon-13 is put back into the atmosphere. And this is the evidence that we have suggesting that this impact of carbon is largely from the fossil fuels that we're burning. And the modern rate of change is very quick. And that's problematic because one of the things we're going to see is that there's a little bit of lag between when the temperature warms versus when the carbon was put into the atmosphere in the first place. So when we look at some key points here when we're talking about greenhouse gases, well, the first thing to know is space is cold, right? Remember when the Star Wars movie where Princess Leia was floating out in space and she was doing her flight across there? That was the goofiest scene in any event, and she froze. All right. So space is cold, and the greenhouse gases help us because they're relatively transparent to incoming visible light, meaning that the wavelengths of energy that are transmitted from the sun don't interact as greatly with the matter in the atmosphere on their way in as they do when they're radiated back out after they've interacted with the matter on the surface of the earth and their wavelengths have changed, right, typically to longer wavelengths, then they have a tendency to interact more with the matter in the atmosphere and get trapped, right? It's good in the sense that historically that has kept Earth habitable, especially over the last 10,000 years. But even looking across all those cycles, those greenhouse gases have been very important to keeping the Earth habitable even during the relative cold periods. However, the more we increase carbon dioxide, again, which again, 78% of our footprint in terms of greenhouse gases is carbon dioxide, this is going to trap more heat at the surface, which is going to cause warming. Okay, it's going to cause that radiative forcing, and that's going to warm our atmosphere. All right, so if we look at the isotropic signature of carbon emitted by fossil fuel combustion, is it lighter than the signal of pre-industrial atmospheric carbon, heavier than that signal, or the same as that signal? Well, it's lighter because remember, fossil fuels are old plants, and plants discriminate against the heavier form of carbon when they're building their biomass. And so consequently, what we're burning has more of the lighter version of carbon in it. So ICE cores provide data on, and you can select all of these that apply here, right? So the difference between the measured versus the standard of oxygen 18, which is a proxy for past atmospheric concentration of atmospheric CO2 concentration. That same thing, which is a proxy for past temperature, direct measurements of past CO2 concentrations in the atmosphere, the difference between measured and the standard for deuterium, which is a proxy for past temperature, or direct measures of past temperature. Okay. So we know it isn't E, right? We weren't around during those times to take direct measures with thermometers or any other devices. All right. So you can rule E out. So let's look at these other ones. Well, B, clearly, oxygen we know is a proxy for past temperature. C, we can measure directly the concentrations of CO2, recall, from the gas bubbles trapped in those ice cores. And D, the amount of deuterium, right, relative to the standard, which is a proxy for past temperature. So those three we know is a good past. Those are good measures. A, on the other hand, oxygen isn't really a good proxy for past atmospheric carbon dioxide. It's really only a proxy for temperature. Okay, so B, C, and D. All right, so what are the current trends? Well, when you look at temperature, right? This graphic down here, I've circled the kind of where we are now, right? So this is kind of the end of that. We're only going back here about 4,000 years. I'm sorry, 400,000 years. So about half of what some of my earlier graphs showed you. But you can see here we are right down here on the end. So here's our temperature profile, right? And it's fluctuated during this time. There's been quite a bit going on. But here, again, we're going back right here. You can see where zero is. And I think this date, I didn't put it on here, but I want to say this dates back to about 2018. Um, so you can see here's zero. Let's say that's 2018. This represents, well, this would be 25,000 years ago. So this would have been about 10,000 years ago, right? Remember, we're coming out of the ice age. So this would have been in that last 10,000 years we've been down around here. And as we get closer to the current age, watch what's happening to carbon dioxide, right? It goes up exponentially. Okay, so it's not a linear slope that's just a straight line. It's an exponential or J-shaped slope, right? I like J-shaped slopes, those exponential slopes in my bank account. I don't like them so much with carbon dioxide. But notice that the temperature hasn't reacted the same way yet. So currently, our carbon dioxide levels are between 417 and 419 parts per million. All right. This is higher than it's been at any other time in the last 800,000 years. At this current rate of increase, we expect that carbon dioxide is going to be over 670 parts per million by 2100. Why is this important? Because the estimates have been anything over about 450 parts per million is going to start kind of a catastrophic decline in terms of the stability of the climate. Remember, stability is the thing that's allowed us to maintain agriculture over the last 10,000 years and has led to our ability to survive very comfortably on the planet with a level of technology that's been unprecedented in human history, especially in the last 150 years. That, as I said, is going to result in an increase of maybe as much as 4 degrees Celsius due exclusively to this greenhouse effect. Again, predominantly because of carbon dioxide, but as this warming occurs, we expect that there are going to be an increase in other greenhouse gases like methane as well as more of the permafrost continues to thaw. That is a significant concern, right? That's one of the reasons that agriculture, particularly livestock and how we manage livestock, as that has continued to increase as there are more people on the planet and more of them are meat eaters than plant eaters. That's resulting in more methane to the atmosphere as well. Well, I want you to recall as you're looking at this graphic that the difference between remember our average temperature of about 59 degrees Fahrenheit, 15 degrees Celsius, and a deep ice age is only about 5 degrees Celsius, right? That's the magnitude of change that results from just 5 degrees, 4 to 5 degrees of change in that average temperature. So if we're talking about 3 to 4 degrees change the other direction, what's that going to look like? Well, there's something else I want to point out here because there are a lot of people out there that don't study this science that say, yeah, climate change, well, it's going to get a little warmer. That's okay. The problem here is that there is a lag effect, and that lag effect is at least 40 years typically between when you see a change in the amount of carbon in the atmosphere and when you see a temperature change, right? So when we look at those ice cores and we look at modern data as well, right? So now we've got our historical record through those ice cores, all that proxy data, along with direct measures of CO2 from the ice cores. And we've got direct measures that date back into the 1800s. And we've got measures of carbon dioxide that go back, good gosh, I forget how long, but well into the 1950s, I know, and I think prior to that. So we have a lot of data. And what we see is a pretty consistent lag between when carbon dioxide changes and temperature changes relative to that. Now, if you've ever looked at in ecology, two species interactions where, when you have an increase in the amount of prey, you typically have after that, after some lag period, also a likewise increase in the amount of or the number of predators, right? And as the predators increase and they have a bigger impact on the prey, then the prey starts to decline and then the predators start to decline, right? Well, this is somewhat similar in that sense. So here where we have a change in carbon dioxide that occurs, what we see is that after that, we see an increase in temperature that corresponds, but it doesn't happen at the same time. There's a lag here. So I put this yellow line through the peak of carbon dioxide and this red line or orange line through the peak, the subsequent peak of temperature. All right, so you can see here was a relative warm period, about, what is that? Oh, somewhere in the neighborhood of 140,000 years ago. 140 to 130,000 years ago. All right, now look where carbon dioxide, remember this? This guy up here, look where it is now. But see, our temperature hasn't moved a whole lot, and that's because there's that lag time that we haven't worked through yet, even in my lifetime. We're seeing changes, but it's where the magnitude of temperature changes is not nearly where the magnitude of carbon changes, right? And in fact, that's true with all of these other gases as well, right? That's the same, you see the same curves, the mirroring that occurs there. So you can see why we're so concerned. So this kind of covers what I talked about previously. But why? Why do we see this lag? Um, this has to do with interactions between the ocean, which is a tremendous sink for a whole variety of things. Okay, it's a sink for carbon. It's a sink for temperature as well. Water provides a huge stabilizing effect on the Earth's surface. It also, again, moves that temperature around. That's part of the mechanism of stabilizing temperatures. But generally, it acts as a heat sink. Remember, we talked about sinks and sources. Okay, so it adds as a sink that then redistributes those temperatures. And the oceans take time to heat up. So here we see approximately a 40-year lag between when we see changes in carbon dioxide and when we see changes in temperature of the oceans. The oceans then subsequently warm the atmosphere. The problem here is that CO2 is a greenhouse gas, right? And this delay doesn't change these certainties, right? We know that carbon dioxide uh, creates this radiated forcing, okay, along with these other greenhouse gases. We know that our impact in terms of these greenhouse gases is the most significant with carbon dioxide. We have the most control over that. So this is the conundrum. This is the thing that we've got to work through is how do we reduce our carbon dioxide footprint, um, since that's the thing we have the most control over, and that in turn is increasing our impact on the warming of the Earth's surface. How do we do that, right? So that's what I want to pick up with next time. I want to look a little bit more at what's going on locally here, and then we'll continue to unpack this issue. So thank you as always for your attention, and I will look forward to seeing you next time.